everyone. Thank you for the warm introduction. This week, in fact, I have started working at Bastille. Over the past 3 years, I've actually been working at Edis Research. So I'm quite passionate about software-defined radio, and today I'd like to show you some of the experiments that I've conducted over the past year. Good suggestion. So let's kick it off then. I'd like to talk to you about spectrum monitoring, drones and first-person video, vehicular keyless entry, and in particular Multipath. Just to get a show of hands, who's heard of Multipath when it comes to radio propagation? Alright, good. So hopefully I'll be able to show you how one technique that you can use to actually visualize it and make it look pretty. So spectrum monitoring, well, fundamentally it's all trying to detect what signals are out there, what portions of the radio spectrum are in use, who's using them, what sort of signals are out there. And a couple of years ago when I was in Vegas, rented a car, and you can usually tell which car I might be driving because it has some extra antennas connected to the roof there. So if you were to look a little bit closer, you can see that there are a variety there, and got some whip antennas covering different frequencies, but also GPS mag-mount antennas connected to the roof. So inside the car then, you've got the laptop, and in this instance I borrowed some hardware from my former employer, and there we have the BT100 and X300, just two different radios sampling at different frequencies. And you can, for example, write some Python code. Python code is great because it's easy to play with and modify quickly. This actually interfaces to GNU Radio, and GNU Radio has an interface to talk to the hardware. But this particular program then, it was just set up, I sort of wrote it bit by bit as I was going around this road trip to scan the spectrum, go through it bit by bit, and actually record and log the energy signatures that were detected at each step. So you would go through, and on the left-hand side here, you could see that when it does one particular iteration, it logs the GPS coordinates where that data was collected, and it tells you what frequency, what gain settings, how long it took, how many FFTs were processed, and it does this over and over again, and you can configure what range of the spectrum to actually go through. So I want to do the entire thing, and in Python code it just looks like this. When you want to configure it to scan a particular range, you can configure it and then specify what ranges in the radio spectrum to look at. And it will just go through, and it will also plot them if you like. And it's just really interesting to see the sort of signatures that various communications protocols have on this sort of FFT plot. So this one here is at 1.8875 gigahertz. So this is in the cell band. And you have these three distinct lines here. The blue one there is the sort of average energy. So you capture at that frequency for a period of time, and then you do the Fourier transform, so you turn it into the frequency domain plot, and then you basically take the average over each of those successive windows. And then the red one there is the peak energy in each of those frequency bins, and green is the minimum, or the lowest energy in those bins. And usually you would just look at the average, but if you have the maximum and minimum, it's also very helpful because you can see if a signal is on all the time or if it's bursty. So if there's some communication systems that only send out energy every so often, obviously you'll have a maximum amount. The average would be a little bit lower than if it was on all the time, but your minimum would actually be at around the noise floor. Whereas if it was transmitting all the time, your minimum would actually be elevated to around about the same level as the other ones. So you can see here, this is probably some bursty cellular signal. And the plot there that's obscured on the right-hand side is the time domain plot. So that's just the magnitude of the signal, but all that interesting in this particular context. And then as you iterate through, you see that it will animate the display, and that looks like this as it goes through the frequency steps. And these ones are all captured from the cell band. And because it's also storing the GPS coordinates, you can take those and then plot on the map at each point where you captured some of your spectrum. So you could go around essentially like in the old days of war driving, where you would hook it up to a GPS. In this case, you're storing spatially the spectrum at that particular point, and that can give you very interesting clues about what systems are in use, but in particular, spatially, where they're based. And you could go on and process this data more and perform localization if you wanted to. And if you don't want to just capture absolutely everything, you can also do other tricky things like energy detection. So you might say, well, I want to capture the notion of my idle spectrum or a silent spectrum, and then any signal that pops up and exceeds some energy mask that I've defined here, so in this case it's in blue, see how it's kind of flat, anything that exceeds that will be marked in red, and then you can see, hey, something's actually popped up, there's a signal there, I'm going to store that, and then I'm going to analyze it later. And then when, in this case, it actually detected those signals, you can see that it found this hit there, and it stored that information, so you can process that for later. So this is just like a generic tool for looking at the radio spectrum, and what's nice is that as you end up doing this sort of sequential scanning, you can store these individual captures, and then you can stitch it into one really, really wideband FFT there. So here we're looking at, what's this? We're looking at the two regions of the cell spectrum allocated. This is in roughly the 800 megahertz region, and this is in the 1.9 gigahertz region. And you can see that each of these individual sections are one capture. You can record all of that and then run the Fourier transforms and stitch them all together into one continuous thing. And although it's not real time in this case, it gives you an idea of how the spectrum is allocated and all the different sort of protocols and communication systems that are out there and how they actually are organized in the spectrum. It's one thing to, say, look at the FCC's database and see notionally how the FCC has agreed to license the spectrum. It's another thing to actually go and look and see really how it's being utilized from a day-to-day perspective. And also, even if you measure stuff over the course of the day, you can also correlate it with human activity. So maybe during peak hours, there'll be more activity in the spectrum than at other hours. It's just interesting to see how human behavior can be actually captured in the radio spectrum. This is a wider FFT, stitched FFT here. This is actually the 2 to 2.5 gigahertz portion of the spectrum. So ISM, 2.4 gig Wi-Fi, and you can see all of the sort of Wi-Fi traffic and Bluetooth traffic popping out there. So that's sort of the generic analysis of the radio spectrum. You can also do other clever little tricks, and I'm going to do a shameless plug. I'm going to go into this in a lot more detail on Friday if you want to come along to the Wireless Village. But instead of just looking at the frequency domain, so how the radio energy in the radio spectrum is distributed through the frequency domain, you can actually look at this thing called an autocorrelation plot. And what this is doing is it's trying to analyze a signal to see if there are repetitions inside that signal. And that can be a really important clue as to what sort of signal that actually is. So here I've done this for-up of all of some of the major popular cellular standards that are out there. So you've got GSM for the first two and LTE for the second two. And this for 3G CDMA. And each of these systems tend to have, especially on the control channels, repeating information. So that when you turn your mobile phone on, it has to find a network, right? And it has to try to find some known information out there that it can actually identify as a legitimate network and then say, oh, I'm going to start getting information about the network, synchronize to it, and figure out what's going on, and then I'm going to subscribe and actually get on as a legitimate subscriber. So here, if you look at GSM, then it has these characteristics peaks. And the way you interpret this kind of diagram is that you look for the first major peak that pops up. And that's telling you that there's something in your signal that repeats with that period. So there's a more obvious one here for LTE. And maybe you can't quite see it, but this first major peak actually appears at exactly 10 milliseconds. And if you were to do the same thing for 3G CDMA, then you will also get a really strong peak at 10 milliseconds. And if you actually look at the standards, that's the rate at which the system sends out this same information, this repeating information about the network. So it's a fixed bit of information that your cell phone will try to find and then look up here. And so if you have some unknown signal, you can put it into something like this, And if you know the standards, you can say, oh, well, that's repeating at this rate, or that's repeating at that rate. If you were to hook this up to GPS, you would have a peak sticking out at 1 millisecond, because that's the rate at which their CDMA code wraps around for the civilian access code. So it's another little hint about what a wireless system is doing. So some cool tools that you can use just to give you a flavor of what's going on. So let's look at drones. Drones are pretty popular, and a friend of mine egged me on to sort of get into it. And I thought it would be cool to look at how they use the radio spectrum, and also to see maybe you could actually put an SDR onto one of these babies and fly it around. So the background here, we're actually looking at the 2.4 gigahertz spectrum, where people are actually using their remote controls to fly these drones around at a drone meetup. And these remote controls use frequency hopping, so you can see that you end up having these little packets that aren't transmitted on the same frequency all the time, but they hop through the spectrum. And this allows for lots of people to be using this same band at the same time. So it means that you don't have to individually allocate a particular frequency to a person. They can all hop through this region, and if all goes to plan, they won't interfere with one another. So it's a really effective way of sharing the radio spectrum between multiple users. So I went out there and used a B210 there to capture that radio spectrum. Apart from the uplinks from the remote control, it was also interesting because with first-person video, they mount cameras onto the drones, and they send that video back down over the air on the 5 gigahertz band. And they actually transmit, remember NTSC, the old analog video standard that has been shut down in favor of digital broadcasting? They transmit that as NTSC over FM. So it's very, very wide band, and then you do need to allocate these individual channels lest the competitors trample on one another. So I thought that was interesting. And Make magazine did this little piece when they actually do the drone competitions, so you can see they really take off and are very nimble. And there are these amazing pilots here that have the first-person vision goggles on that see from the point of view. So it's pretty intense. And so I thought it would be interesting to see whether or not you could do this with SDR and do it digitally. So I, with my former employer, got this drone, and I was really excited. I had never flown one before, and actually I don't have the audio plugged in, but I make some very loud and excited comments when I manage to get it taken off. But they're really cool. If you haven't had the opportunity to fly one, I recommend it. It's there's a lot of smarts in the autopilot, so if you fly in stabilized flight mode, it uses GPS and accelerometers and so on to give you a very stable flight. It's a lot of fun. But the cool thing is that it also has a downlink, so if you run this software on your laptop, it'll plot where your drone is and tell you stats about it. You can see in the bottom left-hand corner. And Edis Research makes this USRP E310, which is like a normal SDR like this, but it's in a tiny little case, and it's actually a self-contained software-defined radio and an embedded PC, like a cell phone class dual-core processor in the one package. So that actually runs Linux, GNU Radio. You can run OpenBTS as a base station on there. But in this case, I thought it would be interesting to put first off a Wi-Fi dongle in there and turn it into a flying access point. So I believe there is supposed to be audio. Is this the audio? Yeah. It'll help if do I need to twiddle any knobs here? And you can see here on the right-hand side, the spectrum monitoring code is running. So remember that spectrum monitoring code that I was showing you? That's now actually running on that little device, flying in the sky. So I've associated my laptop with that AP in the sky. Running FFTs and computations. It's cool because whenever you want to receive radio signals, ideally you want to try and be as high up as you possibly can. Now, that usually means either erecting some sort of really large antenna mast, going to the top of a tall building, and usually getting roof access can be a bit problematic. You have to be creative. Or you can the drone and fly it much, much higher and do your collection up there and then bring it back. So here, this is running the code and then sending the results down in real time to the ground while you're flying the thing. So here's a screenshot what's interesting is that this was the measurement of one particular frequency. Remember how I was talking about the average line? And when I flew the drone up in the air, then I got a 20 dB increase in that signal level. And that's purely because you're up high and you probably have line of sight to your transmitters of interest. So the second part of this was that if they're doing FPV and sending video down on really old school wideband NTSC over FM, and they need to allocate these channels, then maybe there's a way of doing it digitally. And there are commercial solutions out there that do, full HD. They're expensive. I just thought it would be nice to look at an SDR solution. So put a webcam on there and plug the webcam in via USB into the E310. And then wrote some GNU Radio software to actually take the frames of video, transmit them over the air, and then receive them on the laptop, and then get a live video feed. So this first iteration was just using GMSK, very simple. And you can see the video frames, they're being broadcast on the radio spectrum. So just very quickly, this is the prototype, very first flow graph. It takes in the raw video frames, which have been processed here, and then this construction here either takes frames if they're available and modulates them, or it just puts a pseudo-noise code onto the stream so that you're always transmitting something. And this means that your receiver can have a signal to lock onto all the time. And then it just sends it out the user. On the receiver side, it's a very simple demodulator. And then it outputs those raw data frames out in this small code that defragments it and displays it on the screen.
Got a laptop here and a GNU radio.
That's what it looked like there, just a laptop receiving it.
And right over there is 3D Robotics.
And the drone there set up to receive.
Drone. There we go.
And they're really, really noisy. They sound like a big mosquito. So it would be very, very easy and quick to understand why people would get really annoyed by them, especially when one floats into your backyard. And it's kind of scary because this is the video link there. You can see it transmitting the video. In this case, the first iteration was sort of lower frame rate. But when I gave it some significant altitude, you could essentially see into everyone's backyard. So, again, this brings about notions of privacy.
And there we are in the image.
And you can get some serious altitude with this.
Are we going further and
further? But be careful where you fly and when you fly in relation to airports and other restrictions. And you can see the altitude there that it's coming out, and you can see that. So that's the radio spectrum coming down there in the GNU radio receiver, and you can see in the little image there quite high, and that's us there. And then once you're up high, you can see people's backyard, and that was at 25 meters up in the air, as reported by the app. So some cool things you can do with drones. I had a GoPro strapped to it. So that's in HD. And the latest iteration, obviously, I'm working on other interesting things now, but it was in a state where you could do full HD from the drone, which is pretty cool. And a little side note, these drones, they can be a lot of fun, but they can also be problematic. Can I get a show of hands just out of interest? Who's heard or watched any of the Cyber Spectrum SDR meetups, apart from the one person down there? A couple of people? Yeah. So this is my good friend Austin. You might have heard about the ISE3 reboot mission that occurred just over a year ago now. Austin and I worked on that. He was the lead engineer for that. And he came along, and we were leaving the workplace and looked outside, and there was this beeping, flashing thing flying straight up in the sky at high altitude. It started beeping in increasing frequency, and we just watched it travel, and then suddenly all the lights went out and just fell to the ground. So this drone had an old version of the firmware that had a flyaway problem, and it probably had flown for miles and miles and miles out of the control of the original users, ran out of battery, and fallen to the ground. Now, drones are supposed to have a fail-safe feature that enabled them to land safely when they reach a low battery condition. We got in the car, raced around trying to find the thing, found it, hooked it up to the laptop, downloaded their software, checked the settings, and they had set the low voltage battery fail-safe feature to 0.1 volts. That's not exactly gonna work. And we thought we'd be nice and look at the black box recording of the track and maybe try and take it back to them in the nicer 3D Robotics autopilots, they store that to the SD card. This unfortunately had no persistent storage, so we took the whole thing apart and discovered that we couldn't do it. So sorry to whoever flew it, but it was probably a long way from home anyway. So that's that. So vehicular entry, this is something I'd looked at before. You probably all know that in modern cars like the Toyota Prius, you can have the key fob, you walk up to it, there's some sort of transaction that takes place, and magically it unlocks, you can get inside and drive. A colleague had this car, and I wanted to have a look at really how this transaction took place. So here, he has his fob in his hand, and the car is continually broadcasting a broadcast message over low frequency, and the remote control has a 3-axis low-frequency pickup, so that when you get close, it'll detect this message and then initiate a transaction, a challenge response. So the response is sent back over UHF, as it would be if you press the button on the remote control. But in this case, I just wanted to look at both sides of the link to see how that transaction actually took place. So there I've got an X300 there, which is listening on the LF from the car. You can see I've just got this really, really high-tech LF loop antenna that's shoved into the door handle, and then the UHF is being picked up on this whip antenna there. So if you look at that, Boardline, really great piece of software, written by Eric Olson, really great for signal analysis. If you pop it open there, you can see in the frequency domain, the LF, and interestingly, in the time domain, you can see that there are just these sequence of pulses that it sends out that encode some sort of broadcast information that's specific to the car that the key fob is listening for. So there's some wake up that occurs. If the key fob is near, then an ID is sent to the key fob, and then a challenge is sent to the key fob. Separately, the key fob is responding to all this, but this is only looking at one side of the link. So in the frequency domain, for the UHF response from the remote control, you can see there that they're just a series of energy bursts that also encode data in a similar way. So if you look at in the time domain, where you had that ID, a wake up and a response, a challenge, this is some sort of ID, and acknowledge, and then the cryptographic response. And when the car receives this, it authenticates and thinks, oh, this is a legitimate owner, I'm going to open my door. Now, the cool thing is that with software-defined radio, you can actually look at both these links simultaneously and see how they line up in time. So in this case, I'm running Boardline, but with 2 radio inputs, and it's actually putting both frequency domains in different colors on top of one another. So if you look at that in time, you can see that the blue there is the LF challenge from the car. It's very periodic. And then the red there are slightly off frequency, but you can see here that there's some sort of transaction happening. I'll show you that a little clearer in a minute. And they're the individual frequencies in GNU radio. So here it's just a USRP source with 2 channels going into the Boardline sync. So if you look at this in GNU radio and time domain, it looks like what we saw in Boardline. And then there's the challenge. So in this case, I wanted to set up a relay to see if you could actually relay it over IP. I had a feeling it wouldn't work for very obvious reasons, but I just wanted to try. So in this case, we're pulling in the low frequency. We've got a Hammond up converter hooked up to a B200, and this B200 is actually going to send back the UHF from somewhere else. And you probably heard people using amplifiers to do this, and that's the reason why you should put your Prius remote control in your fridge, in your freezer. But inside now, we've got this X310, and that is going to actually now broadcast inside what the car is broadcasting outside. So it's going to repeat it inside. And then there's a loop back to test whether it's working, which is this. If you put the remote anywhere around here, it's going to think that it's next to the car, transmit some sort of response, which is going to be picked up by this board. So if you put the remote there, it's going to get the LF, transmit back to UHF. And then as VNC did the laptop outside, the wake up was coming through. I won't go into these details too much, but what this is doing is it's looking for energy bursts. So basically, if the spectrum is idle all the time, it's not going to send anything. But when it comes alive with one of these challenges or a response, then it starts capturing, waits for it to go idle again, and then just transports that block of samples and sends it to the remote site. And so that's what's happening here. And same business there. This is now inside, so you can see there that the low frequency stuff is coming in, and this peak holder shown that the remote has actually picked that up, and it thinks it's next to the car, and it's broadcasting back its UHF response. So that was a good step because the remote thinks it's next to the car. The question then is, does the car think that the remote is next to it, and will it unlock? So this is the same sort of relay, but for UHF as well. And then outside, the laptop there is showing that the UHF is being correctly sent outside and being rebroadcast properly. And again, this is just the test run. I had a feeling it wouldn't work, but I just thought, who knows what might happen. You can see there that it's popping up. This is the remote control responding, and all this excitement, I ran outside. Maybe, who knows? And of course it didn't work. Which is good, right? Because it means that they did the security properly. Who can tell me why it didn't work? Yes. So it timed out because the latency of the overall relay was far too long, which is good. This is what you expect it to have. So if you look at it in terms of the timing of a proper transaction when the remote is next to the car, you can see the blue is the low frequency, and the red is the response from the remote control to that. And you can see that they happen in very, very quick succession, because that's what you expect when the physical devices are together. And if you look at it in the time domain, you can see, again, that it happens very, very quickly. Now, because I was using GNU radio outside, shipping it over Wi-Fi, over IP, actually later on through Ethernet cable as well, inside, rebroadcasting it, replaying it back, capturing it, sending it back outside, that just adds up latency in the system. And so if you're doing this sort of with general purpose hardware, then you end up exceeding the time out of this transaction, and it doesn't work. Something else you can do is you can do a direct radio to radio, but then you can't do it over the air, because then you actually end up having hard line between two radios to stream the samples back and forth. Now, there's been some other work done by other folks, I think on a different model of car, and that took things further. I sort of abandoned it after this because I had other things to look at. And it was more about just looking at the transaction in the radio spectrum. But there are other things, other interesting avenues you can do to try and fool the system. But that's just sort of giving you an idea of how one of these other popular communications protocols are implemented and what it looks like on the radio spectrum and how you can actually visualize that yourself. So I'll just talk a little bit about Multipath now. Multipath is always a problem in deployed communication systems in the real world. A lot of the time when people talk about wireless systems, you can talk about it in a theoretical context, in a lab. When you end up deploying a real wireless comm system out there in the real world, you have to end up dealing with all sorts of additional effects that can degrade the performance of your system just due to the fact that you have lots of buildings in the way, or you might be moving at speed relative to the transmitter. So, Doppler effects and reflections, RF reflections, and so on. So, I thought it would be interesting to try to visualize Multipath using a really common signal that's out there. And this one I chose as ATSC, Digital Television Standard for America, North America. And like you saw in the spectrum monitoring code earlier on in the talk, here I'm actually using that same code to capture some TV signals for a period of time. And you can see that you get this very distinctive shape in the spectrum that indicates that it's digital TV. And you can tell because it has this sort of flattish shape here, but then you have the spike, and that's known as the pilot tone. So you can tell if you're looking at digital TV, because on the left-hand side you'll always have this pilot tone. It's just due to the way they do the modulation. And Tektronix has a really nice application note about the fundamentals of 8VSB. 8VSB is the modulation they use for digital television. It's 8 vestigial sideband. And the way it works is that you have your transport stream that contains your compressed digital video, and in the end, after some processing and interleaving and forward error correction, you map it to these voltage levels, they call them, from -7 to +7, and that's how you map them to binary symbols. Now, as your ATSC signals are transmitted, you get all your data sent, but every so often you need to send a known repeating sequence. Remember how I mentioned that with the autocorrelation? For digital television, you have to have this known sequence because your TV sets have to know how to recognize a digital TV signal. It has to have a known sequence that is defined in the standard. So if it says, oh, this is going to be this long sequence, I can lock onto it. This is going to be the beginning of the stream from this point, and I'm just going to keep receiving from there. So every so often, in your ATSC signal, there's going to be this sync segment, but more importantly, there's going to be this long synchronization series of symbols that's used by the TV to assess the state of your channel. So there is an equalizer in there, and that will be used to mitigate against multipath effects, because multipath basically means, as you'll see in a minute, you get lots of different versions of the signal arriving at different points in time, and that will actually degrade your signal because you're receiving the same thing, and they're all going to destructively interfere with one another. What an equalizer does is it undoes that effect, so it does its best to sort of cancel out these other signals that come in, and you just get the one stronger signal going into your television, and then it decodes. But it has to have some fixed training sequence to compare against, and that's what's in this 511 symbol long equalizer sequence. And this is known as the PN511 code. This is defined in the standard. You can open up the PDF and it will have it there. And when you take that and I have a little GNU Red Airflow graph, it takes this long sequence and it turns it into the baseband signal. So this is actually what is transmitted over the air. This is what it would look like if you received just that little bit of signal. So if you actually have this as your reference, you can then go and take this, receive a legitimate TV signal, and correlate this sequence against your known TV signal. And what you get then is periodically, every single time that field sync comes through your television stream, you'll get this really strong correlation peak. And this is what you expect. This is positively identifying that we are receiving a good ATSC signal, which is cool. This is what the TV does all the time to receive and synchronize to your television signal. Just think about it when you change that channel button on your TV. It does this in an instant. It's all set up automatically. Now, what I want you to imagine is, I want you to take these, because this is looking at it over time. I want you to take these and I want you to look at it essentially from the right. And so all of these correlation peaks are put on top of one another. And you get this. So you can see surrounding that, this is zooming into one of these peaks and overlaying all of the peaks on top of one another. You can see that the peak is really strong, and then around that it's all really, really low amplitude. And this is indicative of a really good sequence that you can correlate against. Now, if you look at that over time, then you can see you have this really bright red line, which is your correlation peak, and everything to the left and the right is really low amplitude. So there's nothing there. In this case, we're just receiving the direct signal from the television tower, and we have a nice, strong peak. Now, if you consider the direct part there's no reflections, you're just getting the direct transmission from the TV tower. If you have multipath, and this is the experimental setup that we did, you have, say, a longer path and a shorter path, and the same TV signal will travel along the long path and then get to the receiver at a slightly later point than compared to the short path that'll go from the transmitter and then get to the receiver. And you can see here, these are bouncing off. They might be buildings, they might be big hills, some sort of reflector. But interestingly, there's no direct path here because let's say this is another hill and you're on the other side of the hill. So you don't actually see the TV transmitter. So this is the setup that we had. The TV transmitter is all the way up there on Sutro Tower in San Francisco. And our receiver is here on the other side of this hill. And as it turned out, we were receiving the TV signal bouncing back from a hill quite close by and another one further away in the distance. And so if you imagine this is our view, the TV antenna is behind us, and we're getting a reflection off this hill, and we're getting a reflection off this one further out in the distance. So that means we're getting two strong TV signals, which is the same signal, but they're arriving at slightly different times in the transmitter. And so if you run the software again, this is what you get. My friend was actually holding up a TV antenna, pointing it at the closer hill, and then slowly moving it toward the hill further off in the distance. So the software first locks onto the strongest correlation peak, which is going to come from the strongest signal, which is the hill that's closer in, which is here. And as you can imagine him moving it from one hill to the distant hill, this is time on the vertical axis. As he moves it, this correlation peak, which is the strongest signal coming in, will decrease in amplitude because we're not pointing at that hill anymore. And the signal from the distant hill is going to become stronger because then we end up pointing at it. And you can see there that this appears, actually two of them, to the right of the main peak. And so this is offset by whatever, 60 samples, which translates into maybe microseconds worth. But this is actually showing you that you've got one strong signal coming in, and then maybe two other ones here arriving, say, 5 and 7 microseconds later. So this is actually telling you how many reflections you've got coming in to your one point where you are. And that's essentially the visualization of multipath, because you can see all the different signals coming in from the different path lengths that they have to travel through, propagate across, to get to your receiver. And so an equalizer is important because it essentially mitigates against this, all these signals that end up destructively interfering. Now, this is important for this system. If you consider more modern communication systems that use OFDM, like Wi-Fi and LTE, they're actually designed very much with multipath in mind. So they use different sorts of ways to correct against this, and that's kind of the golden standard against which all modern communication systems are designed. This is kind of old school. And the other interesting thing about this is that consider that in this case, we're just looking at two hills, right? The hills aren't moving, we're not moving, everything's going to stay pretty static. So you get straight lines here, because that's what you would expect. I did another experiment where I ended up driving from San Francisco down into the South Bay. And every so often I would capture a bit of the signal at that frequency. And my thinking was, well, I'm probably going to pick up the direct path from the transmitter, but there might be times where I get reflections off stuff, maybe off a hill or a big building. And as I'm traveling down the highway, the distance between my car to the building to the transmitter is going to change, right? Because now I'm moving. So there might be an instance where I end up getting closer and closer and closer to the building that's reflecting the signal. So my path is going to become shorter. And so I might see some extra lines popping up here that are actually diagonal now, because that multipath propagation distance is changing. And it's a little bit difficult to see. I haven't really vetted these results too much, but I think if I zoomed in, there was some little diagonal line in there. So I think there was some effect there. But now considering that the car is moving, you could do other interesting things too, like maybe use this for passive radar. And people have actually done this with different television signals and even with FM radio, where you compare it against your direct path of the transmitter, but you point your antenna out in the opposite direction, and then you correlate the two signals to see if you're getting any multipath reflections of things out there like aeroplanes. So it's actually a really cool way of detecting moving objects. And there's been some really interesting research done on this. Some people also used it to try to localize, I think, large ships using digital television signals. And there's a guy that's done amazing work called Yuha on this sort of stuff, but also in the context of ionospheric scattering and amazing stuff. So it's just interesting to think about all these wireless signals that we use every day and how they actually propagate through the real world. So if you zoom in there, you can see that you kind of have these diagonal lines showing up because I was moving. So there was some sort of multipath effect happening there. So that sort of brings me to the end of the talk. The meetups that I mentioned before are a monthly occurrence, and if you're into SDR, I encourage you to either join us online if you're not in the Bay Area, or actually even start one up. We could, franchise it out. But we've been running this for 9 months now, and we alternate between San Francisco and the South Bay. And it's just basically a forum where anybody can come along that likes SDR to talk about their project. Much like these conferences, but on a sort of smaller but more regular basis. And we stream them online, live stream and record them in HD. So it's all online. It's all sort of free and open. So if you're interested in that, get in touch or start your own. And thanks for your attention. So, any questions? No? If you want to come along on Friday to the Wilds Village, I'll go through how to do some blind signal analysis and try reverse engineering signals. On Friday, it's in the early afternoon.